Hello everyone, my name is John. I'm going to be talking about the project called PushSwap today. This project will make you sort data on stack with a limited set of instructions using the lowest number of actions. These actions I'll tell you later. To succeed, you will have to manipulate various types of algorithms and choose the most appropriate solution for an optimized data sorting. The rule is that you have two stacks, A and B, and that A contains a set of random numbers and then B is empty. The goal is, in the end, you will have to sort A in ascending order. These are actions or operations, but I'll call them actions. SA is swap the top first two of the A. SB is the same, just with A. PA is push from the B to A. So if it's PA, then you push to the A. PB is the same. RA, you send the very top of A to the very bottom of the A. RRA is you send the very bottom of the A to the top of A. This is the visual demo, which is going to be easier to understand. So stack A has a set of random numbers right now, and B is just empty. Using SA, 1, 2 is now sorted. Using PB, you send to the stack B. Use RA, RB to send the elements to the bottom of the stack A and B. RRA, RRB, you use it to send the very bottom to the top. And then you use SA in this case to swap the first two of A, and then at last you send PA to make the A sorted. This resulted in 12 actions. Can we do better? I'm not going to talk about this because from the previous video trials I did, and it was abysmal. It resulted in 10 minute, 16 minute. So I'm just going to talk about it really quickly. Okay. So my first approach was iterate through the stack A. I find the minimum value, and then I just send that to the top of stack A using RAs or RRAs. And then whenever I do that, I send that very minimum to the B stack using just simply PB. So B is going to be stacked with just the minimum values from the very bottom. So stack B is actually sorted in the descending order at last. And then at the very last step, I'm just going to use PA, everything back to A, and then A is completely sorted. But this is obviously very not efficient. Stack B, we're just using it, it's just merely a thing to store all these minimums. We're not doing anything cool in a sense, so it is definitely not optimal. For example, if the list was 100, it has 100 elements, and the minimum is like at the very middle or like at the very bottom, then you will have to use like RA like crazy number of times every time you're trying to find the minimum. If the minimum is really hard to find, then you're wasting so many RAs and RRAs. So my solution was, I'm not going to read over these. I'm just going to go to the picture right away. So 2, 3, 5, I'm sorry, 12, 10, all these from the values from 1 to 12 is listed. It's a random number of list. It has 12 elements. I'm just going to find the mid value. I'm going to sort it. I'm going to bring this into the backend. I'm going to sort it using insert sorter quick sort. I'm going to find the mid value, which is going to be, in this case, 7. How I do that is divide the length of the stack A, which is in this case is 12, and then you divide it by 2, then it's 6. And that 6 is the index, 6th, starting from 0th, so 7. I sent everything that's less than 7 to the stack B. In this case, I have to move 6 elements. Okay, and I'm going to call that first chunk. You'll see. So 2, 3, 5 was luckily less than 7, so we just use PB to send everything to B. And then 12 is not less than 7, so we stop there. And then we go to the very bottom and check if that is less than 7. If this were to be less than 7, then we will use RRA and then just use PB to send it. But in this case, it's not. So what do we do here? We simply do RA, and then RA until we find the value that's less than 7. So 6 is less, so we use PB. And then we go on. 9 is not less, 7 is not less, it's just equal. So we just send that to the very bottom using RAs. And then 4 and 1 is they are less than 7. So we use PB to send that. And then that's eventually 6 elements. So we're done. I will call this midpoint algorithm, okay? And we use this midpoint algorithm until we move everything from A to B, or until A has 2 elements left. Okay, so now we have to send 3 elements, which is 7, 8, 9. We do this, Simple. 10, 11, 12. We do this again. 10 is moved. Now we have 11 and 12. 11 and 12 is sorted, luckily in this case, so we won't have to waste SA. If it were to be 12 and 11, we will have to do SA to make that sorted, okay? Now in this B chunk, stack B, we have 3 chunks. I defined the chunks in the red boxes, as you can see. Now we do the same method, midpoint algorithm, but just a little tweak. Anything that's higher than the mid value, okay? So 10 is moved because it only had 1 element. And the thing is, why are these chunks important? Because these chunks are defined as the chunks that are higher than the other chunks the values are always higher. So I know these chunks, inside these chunks, the elements are not sorted. But it's okay, because we're going to take care of the chunks that are above before we go on to the next chunk. For in this case, if this is 978, we're going to do the midpoint algorithm, and then we're going to do this until we have 2 elements left. Then we're just going to keep doing that. If it were to be like 100, we're just going to do 50. We send that 50, and then 50, we send that 25 to B. We're just going to keep doing that until we have 2 elements left, whichever it is on. Like if it's A or B, doesn't matter. If it's on B, we're going to have it descending order. If it's on A, we're going to have it ascending order, okay? But these chunks are important because as long as we take care of these chunks that are above the other chunks, because the other chunks, the chunks below, they're always less than any element from the chunks above. As long as we sort the chunks that are above, these are sorted eventually. So 978, we use same algorithm, midpoint algorithm, and send everything, as I said, higher than the midpoint. In this case, 9. Now we have 7, 8. In this case, it's ascending order, even though it's in stack B, so we use SB to swap that, and then 8, 7, we send that to A using PA. Now we go on to this last chunk, and we find the midpoint, which is 4, and then we send everything. So, but here, I wanted to just talk about this one thing. I did like many video trials to make the video less than 5 minutes, but it's almost impossible, and I can't skip this. So if this last chunk was, let's say it wasn't last chunk, let's say it was like 5th last chunk, then there's going to be other chunks in the below. Unlike we did from A to B, we will have to keep track of how many RBs we used, so that we can use our RBs to bring these elements back up. Because as I said, we have to keep track of the chunk. So after we find 6 and 5 to send it to A stack, because 5 and 6 is higher than 4, which is the midpoint algorithm, we send it, and then in this case, because it's the last chunk, we won't have to. But if it were not, then we will have to use RRB to bring these up, and then in this case it's going to be 4 here, and then 1 above that, so it's 1 4 3 2. We do midpoint algorithm from there again, so that we don't touch the other chunks before we take care of it. So all these letters are explaining that. I won't go through it. Now we have 1 2 3 4 left here. 1 2 3 4 3 2 1 4 left. So we will have to find 4, because 4 is higher than 3. In this case, it was the worst case, so we will have to RB 3 times to send 3 2 1 below 4, and we can finally move the 4 up. And as I said, if it were not last chunk, then we will have to use RB 3 times to bring these up again, and then use midpoint algorithm again, okay? And also there's one more point. So now it's 3 2 1 left. In this case, even though it's higher, even though the number of elements left in the chunk is more than 2, we won't have to use midpoint algorithm, because 3 2 1 is already sorted in stack B as we want in descending order. So this being said, every time you want to do midpoint algorithm, you actually have this function to check if the remaining chunk or whatever initial chunk is already sorted. If it's already sorted, then you don't have to waste any action in midpoint algorithm. You won't have to run midpoint algorithm at all. So in this case, 3 2 1 is just moved PA, and you're done. Okay, thank you very much.